Anyway, if you remember what I said, everything that shows up on the screen is available online already on Polygon site. You've got it over there. You can download all the stuff. So I don't know how you want to take notes or how you want to do it. But I usually go off that as a memory aid, and then I will work on the left-hand side to show you what's really important and what you really need to know. Now, we've gone through all the admin stuff on Aero 420, and you know that you need to get me the groups. You've already got a reading assignment that's on the website, and all the reading material is all there for you to download. It's all there to get started. So we go very fast through this class to start with, because if you try to start in week 3 or 4, experience says you're just not going to make it. The course it accelerates every week. We start using MATLAB and simulating, and we're really accelerating through. All right, so notation. I warned you about notation, but if I were to just highlight the things that are different in this class that you might not have seen before, bold, large letters are matrices. I can't make bold, large on the board, so I use a underbar. It's just like making bold, large. Small, bold is a vector, and I show a vector by. So this is almost always a 3x1 column vector. Almost exclusively for this class, that's what it's going to be. A 3x1 column vector, like this laser pointer. If that column vector is projected in a given reference frame, do we know how to do that? You project the vector onto its components. If you were to do that, then you put it in a reference frame. The reference frame is denoted by a large C with a subscript. So this would be inertial. Make sense? So in other words, if I was to express vector x in the inertial reference frame, I would project the vector x, y, z on the 3 I, j, k axes of the inertial frame. And those 3 components would be vector x in the inertial frame. Now how do I denote that symbolically? Well, I'll say little vector x, and now I use the comma, the infamous BZ comma, which means that whenever you see a comma, the reference frame is coming next. So the reference frame coming here is going to be I, reference frame. That means vector x has been projected onto the x frame. You're going to get 3 components. You're going to get 31 and minus 7 and 4.8, all in the inertial reference frame. And we'll stick with this notation throughout the class, because we don't have to project vector x in the inertial frame. I can project vector, for example, over here, you'll see I have it in CV coordinates. So CV, this will be what we call vehicle carried vertical. That would be a different coordinate frame than the inertial frame. So how would I express vector x in the v frame? The same vector. The same vector would be x bar comma v. Yeah, x bar comma v. That better? Straight up to C comma v. So you can express the same vector x in a variety of coordinate frames. And of course, the next trick is to how do I relate the vectors in one coordinate frame to a vector in another coordinate frame. And to do that, we use a direction cosine matrix. So if I were to express one vector in, let's say, the B frame, from the V frame, so let's look at reference frames. If I race too fast, stop me, okay? So let's talk about reference frames. So let's say I have this vector x in the V frame. suppose I had that extra vector x, and I wanted to put it into the B frame. I wanted to put it into B frame, where this is the body axis. We're going to define all these axes later. I'm just kind of giving you, how do I get vector this into the body frame? How is that done? Well, we use a coordinate transformation matrix, which is called a direction cosine matrix. So we use what's called the DCM, the direction cosine matrix, and my symbol for that is a coordinate transformation matrix. Matrix will have a bar, capital C bold, into B from V. So this is read as C2 from. If you want to remember how to do that, just think of 2 from. 2 from. 2 goes here and the from goes there. So I would take the vector from the B frame and put it into the B frame using that DCM. Therefore, x comma B would be equal to CBV of x comma. Yes? You with me? Questions? Got it? And I can go backwards the other way too. See, I know that x comma b is equal to c v times x comma b. By the same reasoning. By the same reasoning, this is equal to c v x comma b. Well, what does that mean? I got x comma b on the left, x comma b on the right. What does that mean about the product? What does that mean about c v matrix times c v? What does that mean? They have to be identical. So, therefore, the direction cosine matrix going into one frame from the other equals the inverse of going from the other. It's even better than that. If you have an IJK system, when I say IJK, that means unit 1, 90 degrees. If you have an IJK system, the inverse is the transpose. Do you remember the transpose? On the assignment, there's an appendix G. And appendix G is kind of a summary from an old book that I used to use in 320 of all the important things in matrix math. So you can see that appendix G. So, let's take a look at some important reference frames, and I'll quit. Can I erase this? Let's take a look at some important reference frames, and I'll quit. All right. What is an inertial frame? It turns out it's the most important frame that there is. Does anybody have an idea why the inertial frame would be the most important frame ever?
It doesn't move.
With what?
It doesn't move.
It doesn't rotate. It doesn't rotate. So the inertial frame can move, but it doesn't rotate. So if I were to look at the universe out here, the universe. Now this is the universe. Here's our galaxy. Okay, here's our galaxy. And there's us stuck in this corner of that galaxy. Now, don't ask me where I'm at now looking at this. I have to be going to metaphysics. But anyway, all throughout here you got these little reference frames that are floating around. All these triads floating around between the galaxies. They're all inertial reference frames. We call them Galilean. So these are CG Galilean reference frames. So all the Galilean frames are basically inertial frames. There's no difference, but they can be at arbitrary orientations with respect to each other, but they're all floating out there in space. Now why are they so important? Here's the bottom line answer. That's where Newton's laws go. Newton's laws, F equals ma. They hold in a non-rotating order. That's why we call them Galilean frames. So no matter where you were in the universe, I can't prove this because I can't go to Andromeda over here. I can't go to Andromeda and show you Newton's laws hold. But I'd like to, because they do. If I went to Andromeda, Newton's laws would hold just like they do there, like they hold here in the Milky Way. Because they have a Galilean frame. everywhere in the universe. That's why Galilean Newton inertial frames are so important, because that's where Newton's laws come from. Well, for practical purpose, what do? For practical purposes, we say that the inertial frame that we're going to use is approximately equal to little I. Right? And we're going to put our inertial frame over here, I, Ji. We'll put the Ki of the rotation axis. So we have the I, Ji, Ki reference frame that goes along with Ci, little I. And we're going to assume that this frame does not rotate. Now you see that it has an acceleration around the sun once a year. And that's going to throw an error into all of our F equals NA calculations. But the error is out there at 9 decimal places. 9 decimal places. So for practical purposes, unless we're flying to the sun, or flying to Venus, or flying to Mars, in which case we put our inertial frame here at the sun. That makes sense? If we were interplanetary flight, then we'd put our inertial frame at the sun. But since we're interested in Earth reference flight, for airplanes, we put our inertial frame at the center of the Earth. And we assume that the inertial frame does not rotate. Questions? Oh, we're doing so good, I'm going to give you one more then. There'll be one more. Are you with me on this? Okay, let's go one more. We'll go one more deep. At the center of the Earth, rotating is an almost equally important frame. The ECEF frame is also very important. What would ECEF stand for? Earth-centered, Earth-fixed. So now, I've got an Earth, there's the equator, that's the equator, and here I've got the inertial frame at the center of the Earth, and I've got its I vector pointing out into fixed space. And this I vector points to what we call the equinox direction. We passed the equinox on March 21st, and every 3 months we hit one of the equinox points. But this direction is fixed in fixed space. However, rotating around this, rotating this is going to be another I. Will be another I, and that's going to be I ECEF, like so. And the difference between the I and the ICEF is going to be the angle, the Earth's rotation vector of omega of the Earth with respect to I times time, or delta t. That's going to be this angle. So at Earth rate, which is 24 hours every day, this ECEF I vector is going to rotate in the equatorial plane around the vector, and they'll have the common K vector. So the K vector, capital I, will equal the K vector of ECE. The J vectors make a right-hand set. And that's the last thing I'm going to talk about today, is the right-hand set, to nail that down. What is a right-hand set? Before I do, though, is everybody with me on this? One of the reasons the Earth-centered Earth-fixed is so important is because your GPS works off Earth-centered Earth-fixed coordinates. Every GPS set, including your telephone, little phone here, has a coordinate transformation from Earth-centered Earth-fixed to latitude, longitude. It's got a trigonometric solution that takes it, because all the GPS solution comes in Earth-centered Earth-fixed. So Earth-centered Earth-fixed are inertial, crucially important reference frame for our purposes, and that's how we're going to locate ourselves.
In the brackets, is that a T at the end?
Yeah, it should be maybe delta T.
Okay.
Delta, if you want a delta T, you change the time from midnight. You know, these things align at midnight, and then as delta t goes from midnight, the I vector goes away. Once a day, it rotates in the horizontal plane. But your GPS operates off the blue ICEF. Okay? With me? All right, so tomorrow what we're going to do is define some more frames. And here's the hard part we have to do this week. The hard part we have to do this week is to figure out how to derive, this is our goal. Remember I told you you want to be in class? This is going to be an exam. I'm telling you right here. You're going to have to know how do you derive CECEF from inertial. That's a direction cosine matrix. That's a DCM, a direction cosine matrix. How do you derive it? You will need to know not only how to derive this one, all of them. And the only way to get good at it so that you get a good grade on the exam is to practice. You want to practice deriving these things. We'll start doing it tomorrow. Start deriving these things. And of course, your first readiness check already due Friday is deriving a direction cosine matrix. But if you're up in satellite, if you remember that movie Gravity, she's floating around, she's rotating. George, what's his name, is up there floating around. Isn't that ridiculous? I'm going to give you guys extra credit. I'll give you a point for everything. And I love that movie, don't get me wrong. I love that movie. But everything that's impossible or that's wrong, I'll give you an extra point for everything. Now, I'll give you one of them. One of them is, George, what's his name? Clooney. He's flying around in the spacesuit, singing, listening to country music, and that would never happen. One day they don't use those spacesuits anymore, and the last thing you'd let is some idiot flying around space with this thing, using up his gas, flying around the spaceship. Never. Never. So that's one. I give you one. Don't use that on your quiz for extra credit. There's lots of other things in that movie that are incorrect or that would never happen. But again, if you haven't seen Gravity, it's probably too late because you need to see it on the big screen, right? I wish I saw it in 3D. It's a great movie. All right, sign in. See you tomorrow. Thanks.